So today we will derive the expression for bending of a single cantilever. Bending, in other word, we can call it as depression as well. So we will consider a cantilever which is fixed to a rigid support, and I have already explained what is definition of a cantilever. What is cantilever? A beam which is fixed to one end and the other end is left free to apply the load. So we consider a beam of length L. Now, when we applied the load, the beam will undergo bending, that is depression. So suppose if we write the beam as AB, then the new position when the load is applied to the beam after the depression, it is B dash. AB is the beam. When we apply the load, it goes under depression and the new position is B dash of the free end. So the depression in the beam is B dash, and we have to find the value of the depression. We have to find the expression for the depression. So now in the beam which is loaded, we consider a point P which is at the distance x from the end which is fixed to a rigid support. So the distance, if this is P, it will be the either distance, what it will be of? It will be L minus x. So what till then what we have considered? We have considered a single cantilever for which AB is the beam. So when we apply the load, the beam undergoes bending and the amount of bending is BB dash. Next, we have considered a point P which is at a distance x from the support, means from the fixed end. So as AP is equal to x and the length of the beam as already said, AB is equal to L, therefore PB will be equal to L minus x. Now next we'll calculate if something undergoes bending, we understand that the force of reaction it comes into play, and due to that there will be a restoring moment in the beam. So if we want to calculate the restoring moment, that will be equal to W into L minus X, where W is the measure of how much weight is applied to the beam. Restoring moment is equal to W into L minus X at point P. Now what we know, at equilibrium restoring moment is equal to bending moment. Hence at point P the bending moment will be equal to W L minus X. We have taken a beam which acts as a cantilever. The beam is AB of length L, where we have applied the load W to the beam. It undergoes depression, that is bent. We have considered a point P which is at distance x from the fixed end. So the either distance from the free end from point P will be equal to will be L minus X. So we have calculated the restoring moment at point P, that is W minus X, and at equilibrium the restoring moment will be equal to bending moment. So at point P the bending moment is W into L minus X. Now in earlier class we had calculated the general expression for bending moment of a beam. So what we know, that bending moment is equal to Y by R into Ig, where R is the radius of a part of the beam which we consider it is a part of concentric circle. We will draw the figure now. So equation 1 and equation 2, taking both in consideration, we can say Y by R into Ig is equal to W L minus X, and this Ig we know it is moment of inertia. Ig is moment of inertia. Now we will consider another point Q in the beam, and this P and Q are very close to each other. So this distance, a very small change, we consider it is equal to dx. So if we say that this PQ is a part of a concentric circle which makes an angle theta d theta with the origin O, and the radius of curvature is from point Q it is R. So as P and Q are very close, so this length of PO or OP, that will be also equal to R. So now if we want to find the arc length PQ, so this will be dx will be equal to R into d theta, angle subtended by the arc and the radius of the circle, for with which this PQ is part of the concentric circle. So what we have considered, a point Q which is very close to P such that PQ is equal to dx. Now we understand that this arc PQ is a part of concentric circle of radius R and subtends an angle d theta with the origin O. So this arc length dx means the length of arc PQ, that will be equal to dx, and then it will be equal to R into d theta. So now R will be equal to dx by d theta. So this R value of equation 4 will substitute in equation 3. So if we substitute in equation 3, we get, so equation 3 is y by R into Ig is equal to W L minus X, and equation 4 R is equal to dx by d theta. So if we replace the value of R from equation 4, what we get, y, R means dx into d theta, denominator goes to the numerator. So Ig, and that is equal to WL minus X, or we can write it as y d theta by dx into Ig is equal to WL minus X. So we complete the second step. Now first what we have to consider, when the beam undergoes bending, what could be the small change in the bending, and then when we integrate over the whole range, you will get the complete bending. So now what we will do, a tangent from point P and from point Q to BB dash. So this we name it as the point which joins with the bending line, it is S and S dash. So this distance between S and S dash, we consider it to be equal to dy. So we consider it to be equal to dy. Now as symmetry, these 2 points are very close to each other, what we can say that angle SP S dash is also equal to d theta. So now if we consider now dy as a part of a concentric circle which is making an angle d theta with the point P, and the distance is L minus x from point P to any point what you take, PS and PS dash is equal to L minus x. So what we have done? Draw a tangent from point P and Q such that it touches BB dash, the bending line, at point S and S dash. So this S dash gives a very small change, very small value of bending. So S dash, we are writing it equal to dy, and this S dash with point P means SP S dash by symmetry has the angle d theta, which is similar to what made by P and Q at point O. So then we have to find the arc length dy, and also the distance PS will be equal to PS dash, and that will be equal to L minus x. So the arc length dy, it will be equal to L minus x into d theta, or d theta will be equal to dy divided by L minus. So now we will substitute the value of d theta in the equation 5. So what we know, equation 5, so we will substitute the equation 6, that is d theta value, in equation 5. So what we get? Y, this is Young's modulus, d theta dy divided by L minus x 1 by dx into Ig will be equal to W L minus x. So now we will simplify the equation. So if we further simplify the equation, we get dy is equal to W divided by y into Ig is equal to L minus x multiplied by L minus x whole square into dx. dy we have taken in the retained in the left hand side, y goes to the denominator, ig goes to the denominator and dx is multiplied. So, we get dy is equal to w divided by y into ig L minus x whole square into dx. Now, further we can write it as dy is equal to w y into ig L minus x whole square will be equal to L square plus x square minus 2lx into dx. Now, further we will integrate this equation. We will integrate the equation from, if we understand that the total bending BB dash, that will be if equal to y. If we understand that the total bending of BB dash is equal to y. So, we can take one limit as 0 and other limit as y. 0 to y, the length is y. So, if we integrate this equation, y will be equal to this value Wy by Ig, weight, Young's modulus and moment of inertia is constant. So, it will be as usual Wy into Ig integration of L square plus x square minus 2lx into dx with respect to dx. So, if you integrate it, you will get Wy into Ig L square integration of dx x, then x square integration will be equal to x cube by 3 and again 2L is constant, you will get integration of x with respect to x is equal to x square by 2 and the constant of integration, as we have not put the limit, the constant of integration will be c. Now, so your y will be equal to Wy by Ig, nothing is multiply means 1 is there. So, if you integrate dx, you will get x, integration of x square, x to the power 2 plus 1 divided by 2 plus 1, that is x cube by 3, 2L is constant, x you have to integrate. So, 1 plus 1 is x square, means x to the power 1 plus 1 is x square and divide by 1 plus 1 is 2 and then we have constant of integration. So, where c is what? Constant of integration. So, to find out the value of c, we will consider at the fixed end. If x is equal to 0, y is equal to 0 and if you substitute the value, you will get c also is equal to 0. So, finally we will arrive. So, finally from above equation we arrive at y is equal to w y by Ig L square x plus x cube by 3 minus 2L x square by 2 and if 2 cancels out here, then we can just write it as L. We can just write it as L now. We can see from the figure we are trying to calculate the bending moment or the restoring moment at the point P. So, if we consider the whole length of the beam means AB, then the total length, what will be the value? If we consider this P point is at the end, so this x value will be equal to L itself. So, in the place of x, we will substitute L, we get y is equal to W y into Ig L square into L plus L cube by 3 minus L into L square. So, L square into L is L cube and minus L square into L is also L cube. So, this term it will be cancelled out and we can write the expression for bending y is equal to W y into Ig into L cube by 3. Equation number 8. So, this is the general expression for bending in a single cantilever when the beam length is L, applied to bend the beam is W, y is Young's modulus and Ig is moment of inertia. 8 is single cantilever. Equation 8 is a general expression for bending or depression in a single cantilever. Now, again, if the beam is rectangular in shape, what we know for rectangular what we know for rectangular beam, Ig is equal to BD cube by 12, where B is the breadth and D is the thickness of the beam. And if we substitute in the previous equation 8, you will get for rectangular beam the depression is W by Y, Ig value BD by cube, BD cube by 12 means denominator will go to the numerator into L cube by 3. We can further simplify it, 4 will be cancelled out. So, y will be equal to 4 into W L cube divided by y into BD cube. This is equation 9 is the expression for bending for a beam which is rectangular in shape, having length L, B as breadth and D is the thickness of the beam.